Hello everyone and welcome back. Today we're going to do a slightly higher level vector problem, and I'm going to show you some tips and tricks along the way. Something to keep in mind is that the technique I'm about to show you works for all types of vectors. We're going to use displacements, but it works for forces, velocities, and any other type of vector. So let's introduce you to our problem today. This is the ship of Bluebeard the pirate. Bluebeard the pirate, once a year, locates this particular rock structure on shore, lands there, in order so he can check out his treasure and make sure it's still safe. Now, he has two directions he keeps with him in order to find his treasure, and here they are. The first direction is to walk 5 miles at 30 degrees east of north to get to the palm trees. Then he has to walk 7 miles at 68 degrees south of east to get to the treasure. X marks the spot. However, Bluebeard is getting a little old, and he does not want to walk this far anymore. And he has hired you to change his directions from having two lines to only having one. In other words, he wants to be able to walk directly from the rock to the treasure. And in order for him to do this, he needs the exact distance and exact direction to go, because if either are off, he's going to end up in the wrong spot. So to start out, we're going to take a closer look at these vectors, which means we need to draw them. I'm going to start by making a little start point near the rock structure here. The first direction is walk 5 miles at 30 degrees east of north. Now, as a reminder, the last direction stated is your base axis. That is the axis that the angle is based off of. So what I'm going to do, I'm going to have my little start point. I'm going to do a little dotted line in that direction, which is north. Then I'm going to go back to the beginning and mark a 30-degree angle that is east of north. So if this is north, east is toward the right here, which means my vector is this way, and my 30-degree angle is here, 30 degrees east from the north axis. And the 5.0 miles is this vector right here. Now he's at the palm trees, and he needs to walk 7 miles at 68 degrees south of east. Make a little start point. South of east, east is my primary axis here, so I'm going to draw a dotted line east. 68 degrees south of east, 68 is definitely more than 45, so south of east. And here's my angle, 68 degrees, and this distance is 7.0 miles. Okay, so next up, and this rule is actually very important for the entire course. Anytime you are given a vector that is at an angle to your primary axes, you will break it up. You are going to break it apart every single time with any kind of vector. Here, we have two displacements. So in other words, I'm going to call this one vector A, and this one vector B. Vector A and vector B are both on two axes. Vector A is on the positive x and positive y, and vector B is on the positive x and negative y. We need to split these apart and take a look at what's happening on the individual axes. So I'm going to do that visually first. So this is up and right. Notice I'm drawing my components with dashed lines and not solid. This is 30 degrees. So my opposite side, 5 miles sine 30 degrees is going to be 2.5 miles. And 5 miles times cosine 30 degrees is going to be 4.33 miles. On this side, my vector breakup, I'm literally going to use the dashed line I made to actually draw the vector in the first place. So this one breaks right and downward. Again, here's my right angle. 7 miles times cosine 68 is going to give me 2.62 miles. 7 miles times sine 68 is going to give me 6.49 miles. From this point, I actually don't need these anymore. In other words, I'm now dealing with the components only. And to do that, I'm going to bring back my table idea. So vector A, unlike last time, I now have components on both of the axes for both of these vectors. So they're both in miles. Vector A, 2.5 miles on the x and 4.33 miles on the y. Vector B, 2.62 miles on the x and negative 6.49 miles on the y. My totals would give me 6.55 miles on the x and negative 2.16 miles on the y-axis. Now that I have this information, I actually do not need the rest of this anymore. So I'm going to take this, I'm going to put this over here, and we are going to draw our final resultant vector. So I'm going to make a little start point. This displacement vector needs to have an x-axis of 6.55 miles. Again, components are dashed, 6.55 miles. On the y-axis, needs to have a vector of negative 2.16 miles, 2.16 miles. Again, in my drawing, I don't need the negative because I'm literally showing direction with the arrow, which means my resultant vector looks something like this. So Bluebeard needs to walk somewhere in the southeast quadrant, but again, we need an exact distance and an exact angle, which I'm going to place here. Side note, I also could go off the negative y if I wanted to, and I'll show you both. First, I will use Pythagorean's theorem to get the hypotenuse here, which will be 6.90 miles. Then I'm going to use inverse tangent to get theta. So it's inverse tangent, 2.16 miles over 6.55 miles. The units will cancel, and I will have an angle of 18.3 degrees. So let's state this. Here is Blackbeard's new single line direction. From the rocks, he needs to walk 6.90 miles at 18.3 degrees. This is going to be south of east, or below positive x-axis. Now, this could be written another way. This could also be written off the south axis, which means it could also be written as 6.90 miles at 71.7 degrees east of south, or right of the negative y-axis. Either of these answers would be correct. So this technique involves three parts. 1, break down the vectors into their component pieces. 2, combine those x and y components. 3, put those components back together. And the last thing you do is to actually state the resultant vector with the proper magnitude and direction. There's one more thing I would like to state before we finish. These are not triangles. They are vector breakups. Every single one of these you've seen me draw has arrows, and every single one you draw should have arrows. You need to be able to display what direction you are talking about in your imagery. So these are not triangles, they are vector breakups, and all vectors need arrows. And again, in physics, your visual representations, aka your drawings, are extremely important. And like I said, this technique works for all vector types, all vectors. You'll be using this a lot actually with forces, and it will also come into play with two-dimensional kinematics. But for now, I will end it here. I hope this helped you out. Have a good day. This is Mr. M, signing off.